Right, work, energy, and then power. So that's what we have left. What is power is the first thing we're looking at. What is power? Power is the rate at which work is done. You'll have a look in this folder. There is a worksheet on power. It's called the power worksheet. Please print it out, and what you can do is you can just add information to that worksheet. Right? Our formula we use for power is P is equal to W over T, where W is the work done, and work is measured in joules. We know that. When we talk about the work done, we could be talking about WF, which is F delta X cos theta. We could be looking at W net, which is equal to W1 plus W2 plus W3. Depends. We could be talking about W non-conservative, which is a change in potential energy plus a change in kinetic energy. So this W can be any one of those W's. It could be generic, it could be a net, it could be energy principles, depending on the situation. T here is the time taken, and that's measured in seconds, and P is power measured in watts, and it's a scalar quantity, so we don't need any SI units. You also need to understand that in each watt, so 1 watt is equal to 1 joule divided by 1 second, and therefore 1 joules per second is equal to 1 watt. Oops. So it's up to you which SI unit you want to use. Another thing that you should also notice that they do give you is they say that when work is done, you have an energy transfer. And because of that energy transfer, you also need to understand that power is the rate at which energy is transferred. That's just another definition. Essentially, also remember 1 kilowatt is equal to 1000 watts. So that is a popular type of conversion that we look at when we're looking at power calculations. Right, let's have a look here. Example 20. Suppose a boy pushes a 25 kilogram crate with a horizontal force of 200 newtons along a horizontal floor of 10 meters in 4 seconds. The force of friction between the box and the floor is 18 newtons. Right, so let's just have a look here at what information I've got. I've got my forward force. This diagram is a bit... It needs to be fixed. Let me just fix the diagram for you. Right, sorry for this example. Just change all your information. It's all got a little bit muddled up in the printing process. Alright, so for this question, they could ask you 2 questions. I've highlighted them here or added them in. The first question they could ask you is to calculate the power of the applied force. So they want power and they want applied force. So my applied force, F is equal to 200 newtons at a theta value of 0 degrees. And I need power. I need W. Now my work, they don't give me, so I've got to do that. I've got to do work done by my applied force, which is F delta X cos theta. And I need time, and this whole thing takes 4 seconds. Alright, just for spatial reasons, this is how I'm going to sort this out. Power is equal to work over time. I don't have work, so I'm going to say F delta X cos theta all over time, which is then equal to my applied force, which was 200, multiplied by my delta X, which was 10 meters, cos 0 degrees all over 4. And that leaves me with 2000 over 4. And your final answer here is 500 watts, or you could say 500 joules per second. There's your final answer. All right, the next thing says power of the frictional force, right? So let's have a look at that. Again, P is equal to W over T, except here we're looking at work done by friction. So my frictional force was 80 newtons at a theta value of 180 degrees. So I'll then say F delta X cos theta all over time, and that gives me 80 multiplied by 10 cos 180 all over 4, and I'm now left with 800 divided by 4, and that gives me 200 watts or 200 joules per second. Now, essentially, those are the two separate questions they could ask you. They could have asked you to calculate the power needed for the system to function. Alright, so essentially then, because I've got a forward force and a backward force there, I'd have power is equal to W net all over time. Now my W net would be F net, right, delta X cos theta all over time, or if you like method 1, it would have been F delta X cos theta plus F delta X cos theta all over time. Either way, let's say we did do the F net, we'd have 200 minus 80, and you'd have 120 times 10 cos 0 all over 4, and essentially I've got 1200 divided by 4, and that gives me 300 watts, and that would be the amount of power to get the system to function. Right? Essentially, I could have done the same thing here and said 200 times 10 cos 0 plus 80 times 10 cos 180 all over 4. Same thing, 1200 over 4, and I'm still going to get 300 watts. If I look here at my answers in this little zone, I could have also said 500 minus 200, and that would have given me 300. My 500 is positive work done. Power by positive work. My 200 is power by positive work, or minus power by negative work. And that's how I could use that as a minus sum and get 300 watts to get the system to function. So there are three types of questions. They can either ask you A or B, which is each force separately, or they can ask you all the forces together. But the main thing that you need to check is the forces. Are the forces applied force, frictional force, are there multiple forces, or is there just one force? Or is it just one system? So when I'm looking at something like that, you need to understand, you can make these notes that I'm about to do just on the side or somewhere else. Let's say I have this whole thing is a bit of a chain reaction, right? So if I had, for example, this boy, and he was going to push this box, right? What I need to understand is that there is an energy transfer in order for the box to work, right? So the boy himself has an applied force. The applied force has power to it. So that's the energy transfer that I'm seeing. If I had the box and the box was on the surface, and let's say the surface had friction, then as it moves across the floor, right, there is a loss of energy, right, due to friction. So we're looking there at friction, right? Now this energy is dissipated, and we'll look at what we mean by energy that's dissipated in a bit. So that's the two things that's happening. When we apply force, the energy transfer is from the boy to the box. That's the energy transfer, boy to box. When it's friction, there's a loss of energy due to that friction, the difficulty of it having to move across the floor. All right, let's have a look here at example 20. Example 20 says, suppose a 65 kilogram learner starting at rest ran up a flight of stairs 5 meters high in 8 seconds. The speed of the learner at the top of the stairs is 3 meters per second. It says, using energy principles as guidance, right, find the power of the learner, right? That's the question that they're going to ask. So two things now. One, as the learner goes up the stairs, right, we have an increase in gravitational potential energy. All right, there's an increase because she's moving. When you move away from the Earth's surface, your EP increases. The second thing that's happening is, as the learner runs, right, the EK or kinetic energy also increases, because a person started from rest. They weren't moving. So now they're running all of a sudden. You're going to have an increase in kinetic energy. So what we can say then is we can say that the work done by the learner is equal to her change in mechanical energy. Her change in mechanical energy. Now, in this situation, it says use energy principles. So let's have a look at what we've got here in terms of information. I know here that I've got a mass is equal to 65 kilograms. I've got height 5 meters. G I know is 9.8 meters per second squared. V initial is equal to 0 meters per second. V final is 3 meters per second. Time took 8 seconds, and that's my setup. Now in this thing, if I need to use energy principles, then I have to use work non-conservative. Work non-conservative is equal to the change in the potential energy plus the change in kinetic energy. And they want you to find the power of the learner. Now, if I want power, I know that P is equal to W over T. But they're telling me to use energy principles. So I'm looking then at work non-conservative. That is what I need. I've got the time, I need the power, and now I need to look at the work done by this system. Because if there was a change in kinetic energy and a change, so in here what I was saying here is that I have a change in EP and I have a change in EK. So because I have the information for that change, I can use work non-conservative for my work value for power. So I'm going to say P is equal to WNC all over time, where I've got MGH final minus MGH initial plus half MV squared final minus half MV squared initial. All of that divided by time. If you want to do this separately and you want to do it there, you're more than welcome to do that. That is your opinion or your way of doing things. So I've got 65 times 9.8 times 5 minus 0 plus half times 65 times 3 squared minus 0 is all equal to all over 8, and that is 3185 plus 292.50 all over 8. And now I've got 3477.50 divided by 8, and my power is equal to 434.69 watts. And that is how I can get my power calculation. Alternatively, I could have done this separately and I would have had the same thing. 65 times 9.8 times 5 minus 0 plus a half times 65 3 squared minus 0. I would have then had 3477.50 work non-conservative joules, and therefore P is equal to work non-conservative over time, which was 3477.50 all over 8, and that gives me 434.69 watts, and there's my final answer. So you could have done it separately or together, doesn't really matter, as long as you were able to do this type of calculation using whichever method makes you feel comfortable. You can do it all at once if you want. Let's look at the next thing. All right, the first thing was what is power, and the second thing here is they want to know what is the average power needed to keep an object moving at a constant speed. Right, so let's just have a look here. We'll get back to the formulas, but let's have a look here. Suppose a car is moving at a constant speed along a straight road. The car's engine exerts a forward force on the car. The car also experiences a frictional force of opposite direction in the diagram below. When I talk about a constant speed, I must realize that if I had this car, this is what my free body diagram would be looking like. notice that all forces on the object are equal. So essentially, if I have a constant velocity, then I have a situation where my object is in static equilibrium. Right? So if the systems notice that if the car is driven at a constant speed, the magnitude of the forward force is equal to the magnitude of the frictional force. So my force applied must be equal to my force of friction if the car is moving at a constant speed. That is very, very important. It's the whole basis of what's about to happen now. Right? So your engine force and your opposing motion must be equal. Right? So this is important. That means in any situation, right, in any situation that has a constant velocity, I can say that all the forward forces equals the backward forces. So if I know the forward forces, I know the forces that are opposing motion. Right? So in the direction of motion, in the opposite direction of motion, they must be equal to each other. I must have that idea of equilibrium. Now, the average power of a car to keep a car moving, right, is P is equal to W over T. That's normal power, right? But at the same time, what I need to understand is that all forces are equal to each other. So my theta value, right, my theta value is always going to be equal to 0. So technically, I've got force times displacement. Remember, work is force times displacement over time. But I also know that displacement over time is actually velocity. So what we can say is that if I want the average power, my formula is PAV is equal to FVAV. So here PAV is average power. When you use this formula, please make sure you write the formula down correctly. It's like if you don't have PAV, we're going to mark it as incorrect. Average power in watts or joules per second is equal to the force, which is whatever your net force is in newtons, multiplied by the average velocity. Measured in meters per second. Right, so that's your second formula. Now this average power also stands for P is equal to W over T. And I know that the W over T is W net, normal W, work, non-conservative. Still works the same. So depending on what information you have, you can work out the average power using either formula. So both formulas stand for average power. It's just that when you use the PAV is equal to F times VAV, make sure you write down the AV each time because that's important. So how we derive the formula, P is equal to W over T, W is equal to F delta X cos 0 always, which leaves you with F delta X over T. Delta X over T gives you velocity, and that's how we get our power formula. And this formula we can use when we're looking at your forward force and your backward force being equal to each other. So this force that we look at here is F net. There can only be one force. Very, 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 very important. Now let's look at the next little question. Right. Example 22. It says a truck has a mass of 5,000 kilograms, is traveling at a constant speed of 25 meters per second. The truck experiences a frictional force of 9,800 newtons. Calculate the average power of the truck's engine. So when I'm looking at this, I understand that I've got a constant speed. Right. A constant speed tells me that my forward force is equal to my backward force. Right, which means that my forward force of my engine is equal to friction. Alright, so all I've got to do is I need to understand that if I have one of the forces, if I have friction or the force of the engine, then I have force. So my force in this question is actually the force of friction, which is 9,800 newtons. My mass is equal to 5,000 kilograms. And I have a average velocity, a constant velocity of 25 meters per second. And they want power. So I've got force and I've got velocity. I don't have any work or any time. So this works out for me. And all I'm going to say is PAV is equal to F times VAV, and that gives me 9,800 multiplied by 25, and that gives me 245,000 watts. And because it's a scalar, there doesn't need to be any direction. It can be just left at 245,000 watts. That's a basic example. Let's have a look at example 23 here. Right, example 23. It says here that a car has a mass of 800 kilograms. It's driving up a rough inclined plane. Rough inclined plane tells me friction. At a constant speed of 20 meters per second. The plane is inclined at 20 degrees to the horizontal and the car experiences a frictional force of 1,500 newtons. Calculate the average power of the car's engine. Right, when I'm looking at something like this, the first thing I need to look at is what does my free body diagram look like. So I know that I've got going, up the incline here, I've got my normal force. I know that my car itself, I've got an applied force because it tells me it is driving. I know naturally coming down, I have a frictional force. I also know that coming down here, a natural force of gravity, I've got mg sine theta. And across my force of the normal, I've got mg cos theta. So essentially, I've got two things going on here. I don't know my applied force, this force here. I have no information about that. The only thing I have is I have the frictional force, which is going. So what I need to understand is because the car is driving up the slope, then my direction of motion is up the slope. So going up the slope is the force applied, but I don't have information. Coming down the slope, right, there are two forces acting down the slope, right? One is your frictional force, right, acting down the slope at 1,500 newtons. And the second thing is gravity, Fg, or F parallel. So you've got gravity causing the car to go down the slope naturally. So what we can use, that's a better value to use, is mg sine theta. Oops. And that's also going down the slope. Now, if I know the downward forces, if I know the forces, I know the forces up the slope must equal the forces down the slope. That can help me with my calculations. If I know that the car is driven at a constant speed, this is important. My car is driven at a constant speed. I know that the essentially the forces that are up the slope must equal force of friction plus mg sine theta. Alright, so that's going to give me my force for my formula. So my formula is equal to P average is equal to FV average. Right. Let's see what information I have. I know that my mass is equal to 800 kilograms. I know that my VAV is equal to 20 meters per second. I know that my theta of my incline is equal to 20 degrees. I have a frictional force equal to 1,500 newtons. And that's the information that I have. Okay. All right, in this formula, I know I need to have my force. So I'm going to go average power is equal to my force of friction plus my force parallel multiplied by VAV. All right, so now I'm left with 1,500 plus mg sine theta multiplied by 20. So I've got 1,500 plus 800 times 9.8. Those are my two downward forces. Sine 20 degrees, right, times, at that, times 20, which is my average velocity. So I'm now left with 4181.44 multiplied by 20, and that gives me an average power of 83,628.80 watts. So what you could have done also is you could have said, you could have, if you wanted to, work out F net first, which is force of friction plus mg sine theta. And you would have gotten 1500 plus 800 times 9.8 sine 20 is equal to 1,500 plus 2,681.44. And that would have given you 4,181.44 newtons. And that's F net, right? You would have taken that value and said PAV is equal to FVAV with 4181.44 multiplied by 20. And that would have given you 83,628.80 watts. So you could do it all at once like this, or you could have done it separately and you still would have gotten the same answer. If you're comfortable working separately, more than welcome to do that for these types of questions. Right? So make sure you understand the main thing is when I see constant velocity, no matter the situation, my upward forces are equal to my downward forces. And the last thing we're looking at here is the power of an electric motor. Now, electric motors can be used to pump water to the ground level. The water will be pumped at a particular rate through a vertical height. The rate at which water is pumped is liters per minute or kilograms per minute. So that tells me that 1 kilogram is equal to 1 liter and 1 gram is equal to 1 milliliter. I also need to know my conversions. I need to know how to go from grams and milliliters into kilograms or liters. For that conversion, please make sure you say that. I'm going to have to divide by 1000. Right, and I always want my answers to be in kilograms per minute. Right, for example, if an electric motor is able to pump water at 120 kilograms per minute, it means that 120 kilograms of water is pumped to the ground level every minute. So don't forget for the minutes, if they give you seconds, you need to go from seconds to minutes. Right? But also don't forget, if I have P is equal to W over T, then that time must stay in seconds. So if they give you minutes, make sure that you can get back into seconds over there. So that's the basics of power of an electric motor. Let's have a look at some examples, or let's see how this works out. Right, example 24. Calculate the minimum power required of an electric motor to pump water at a rate of 80 kilograms per minute from a depth of 10 meters. Right, let's just have a look here. If they want, what they want you to do is, basically, they want you to calculate the work done by the pump. Okay, I'm analyzing the question, so you can write this down. Work done by the pump in raising 80 kilograms of water through a vertical height. Alright. So what we need to understand here is when we have work being done by the pump, you need to understand that there is an upward force. To get the water from underground, that's the ground, you have water that's here. And now you're going to pump the water up the water pump. There is an upward force, which means an upward force is an applied force. Okay, it's an applied force exerted on the pump. All that means, if I have an applied force, then I've got non-conservative forces. So we're working with non-conservative forces. And I know that non-conservative forces, I know that the work done by a non-conservative force is equal to the change in mechanical energy. Of the water. Okay. Essentially, it means that I can use work non-conservative is equal to the change in EP plus the change in EK if I wanted. So I also know that electric motors pump water at a constant, this is important, at a constant rate. And therefore, if something's at a constant rate, then I must think constant speed or velocity. And if I have a constant speed or constant velocity, therefore there is no change in velocity, which means my acceleration is equal to 0 meters per second squared. And I know that if I have no change in velocity of the water, then there is no kinetic energy. And therefore, my EK must be equal to 0 joules. So when I'm doing this section, whenever it comes to EK and it's at a constant rate, then I know that EK must be equal to 0 joules. I know that therefore I can make a bold statement and say that the work done, this is important, by the electric motor is equal to the change in gravitational potential energy of the water only. So think about it like this. Work non-conservative is equal to the change in EP plus a change in EK. But EK is always equal to 0 joules because of the constant rate that it's being pumped. It's pumped the same each time. So therefore, work non-conservative is equal to the change in EP. Right, and that is what I have there. So that is what is important. So if I look at this question that we're dealing with now, let's just see what information we have and how it's going to play out. I've got a height here of 10 meters. I've got a mass of 80 kilograms. That's my water. I don't know my force. I don't have a force of friction. My velocity is constant. Let's see what that's fine. I don't have a velocity. It's constant. I don't have work non-conservative. I don't have power. And I have time, which is 1 minute, which should become 60 seconds. Okay, so that's the information I have. So let's see how it works out. So WNC is equal to the change in EP, which means WNC is equal to MGH final minus MGH initial. And that gives me 80 times 9.8 times 10 minus 80 times 9.8 times 0, giving me a total of 7840 joules. That's my work non-conservative. That means that, therefore, 7840 joules of work is done every minute to raise 80 kilograms of water. These are statements you have to keep writing so that for the next question you're more prepared as to what's actually happened. What's happened? A height of 10 meters. Alright, so that's the work non-conservative. Alright, so what they want from us essentially, they want us to calculate the minimum power required. So we've got the work non-conservative over there, And we can say therefore, P is equal to work non-conservative all over time, where we have the change in EP all over time, and that's 7840, and the time was 1 minute, which is 60 seconds, and you're going to get 130.67 watts. And that is your answer for power. All right, that's the first thing. That's the first type of a method. Let's say method 1. Find your work non-conservative. If it's a pump at a constant rate, it's just the change in EP. And then once you're done with that, you can sub it into the work non-conservative. Method 2, right? What you could have done is you could have calculated speed, right? Or rather average speed, which is VAV is equal to delta X over T. And you know you're raising it 10 meters, and that whole process takes a minute, which is 60 seconds. And you're left with 1.6666 recurring meters per second. So that's the first thing you could have found. The second thing that you could have found then after that is understanding force applied. So think about it like this. The water is pumped at a constant speed, right? And therefore, the upward force of the pump is equal in magnitude to the downward force. Now water has mass, so that downward force is actually weight, or rather gravity. So basically this is what I've got. I've got my force applied that's coming from the pump, and then I've got Fg here, which is coming from the mass. It's my downward force. So my force applied is equal to mg. And I know the mass is 80 times g, which is 9.8. And I'm going to get a downward force of 784 newtons. And that gives me force. So I've got average velocity and I've got force. So I can say that therefore the average power to keep an object moving at a constant rate or velocity is PAV is equal to F times VAV, and that leaves me with 784 multiplied by 1.666666 recurring is equal to 130.64 watts. So that would have been method 1 or method 2. And that is how you sort out that information. You could have either used this new formula that we're introducing, right? Or you could use method 2, where you can use either formula is a relevant formula for this topic. Right, the next thing that you would look at is in this folder you will see exercise 3. Exercise 3 is an exercise relating to power, but it is a little bit of a complicated exercise. If you want, you can look into the folder that says Work Energy Power Lesson 7. lesson 8, sorry. And in that folder, you will find a video of me going through exercise 3 in detail from question 1 up to question 6. And the memo is also there, so you can go and mark your work. If you are comfortable enough, mark your work. If you are not comfortable enough with this work yet, you might want to watch question 1, 2, and 3 and then try 4, 5, and 6 by yourself. So that will be the next thing that you do. Go into do exercise 3, however you can, whatever method you choose, but the videos and the memos are available in lesson 8, under lesson 8 in the folder. And that's the end of work, energy, and power. There is a little bit of a summary here. The summary deals with work, energy, and power. It looks at work. It looks at formulas for work. What is the definition? When is work not done? The next thing looks at energy. It looks at talking about potential energy, kinetic energy, looking at the work, the two formulas, the work energy theorem, and how we look at mechanical energy in terms of conservation. The last thing is power, rate at which work is done. Looks at the formulas for power, watts and joules per second, and then your conversions of horsepower and how a watt of power is when a joule of work is done per second, or when a joule of energy is transferred each second. And that is your summary for work, energy, and power.